2, and today my presentation is about the mechanisms of different vaccines against COVID-19. So let's begin. So talking generally about what vaccines are. A vaccine is a biological preparation that provides active acquired immunity to the particular infectious disease. A vaccine typically contains an agent that resembles a disease-causing microorganism and is often made from weakened or killed forms of microbe, its toxins, or one of its surface proteins. The first vaccine to be developed against a contagious disease was in 1796 against smallpox by Edward Jennifer, who was a British doctor. So what do we know? So if you're talking about vaccines, so we should talk about like what COVID-19 is actually. COVID-19 is an infectious disease caused by SARS-CoV-19, and most people who fall sick, like they are like mostly who has low immunity, like the weakened immunity, impaired one, and like the symptoms in every person like can be mild, moderate, or severe depending on the person immunity the person is having, right? So let's move on. So now we move to the main topic. So why do we need this vaccine? What's the reason for the development of this vaccine? There are two main reasons. The first one is safety, which is the utmost priority for making this vaccine, and the second is efficacy. Now, if we talk about the efficacy, like it's talked a lot about it in media, and we have to see if this vaccine is effective against to prevent diseases or to prevent infection. What does that mean? It means like if you're talking about to prevent disease, it means that if a person who is vaccinated will get a disease with like COVID positive or not, and if you're talking about the infection, maybe the person who is vaccinated might have like what we say the corona, but he's asymptomatic, he's not showing symptoms. So that's what we have to see from the vaccine. What will it lead to? Either it will lead the person like having asymptomatic, like no symptoms, or he will have no disease, like no COVID. That's all. Move on. Thank you. So now we'll talk about the different phases of vaccines. There are many phases, as you can see: animal testing, phase 1, phase 2, phase 3, and then at the end we go for EUA, which is emergency use authorization for FDA approval. So talking about the first phase, animal testing, which is like talking about preclinical, which is the animal testing. Here what we do, we give the vaccines to the animals, like a rat, mouse, like something like that. So when we are giving the vaccines to the animals, we are monitoring the side effects too, looking if that animal is showing mild, moderate, or like severe symptoms. After we are like when we are monitoring the symptoms, we look for efficacy. If that animal is making antibodies against this vaccine or not. Then at the end we give the virus to the animal just for protection. After this animal testing like the phase went like well and everything is fine with the animal, we move to phase 1, which is actually we are giving vaccines to the humans like small population. We are not giving, because it's our very first time we are giving the vaccines to the people like humans. So we will just look for this small number of people, small sample size, and the people we'll choose should be healthy. So we have to see the people like small population, like you can say less than 100 people, and they have to be healthy. Like we can't give the vaccines on the very first time to the people who are infected. So we have to see if the people who are healthy, and we have to give the vaccine to them. Then, as we said in the preclinical phase, when we are giving the vaccines to the humans, we are looking for the side effects. We are monitoring the side effects. Then there is one more thing about the dosage and its limits. What is it? So there are two limits. Like when we are looking, we are just looking for the upper limit and the lower limit. Upper limit is something when we want to see that a person who we are giving the vaccine to is showing increased number of what we say, increased number of the side effects. So when we give more dosage or upper limit, we have to see what dose the human needs to show severe side effects, and then we look for the lower limit for to see if that lower limit of dose might not result in a human producing any kind of immune response. They might not produce antibodies. So we have to find the dose in between them. Okay, yeah. So second phase is also we are giving the vaccines to the humans, but now we are increasing the people, we are increasing the sample size. Now the sample size over here is from 100 to 1000, and the small sample size in the phase 1 it was up till 100 people, not more than that. So here we have a moderate sample size from 100 to 1000 and 1000. Then when we are giving the vaccines to humans, we are looking for the matched demographics of the population. What does that mean? That means we are giving vaccines to the people of different ages, 18 and onwards. We are giving the vaccines to people who are healthy and who are showing underlying diseases, and people of different races, black, white, Africans. Now here in this we are looking the difference between phase 2 and phase 1 that was before is there we chose the people who are healthy, but here we are just matching, seeing if this vaccine we give to that person and that person, the contrast one, how will that vaccine affect them. So then, as we say, in every phase we'll look for the side effects, monitor the side effects, and the dosage we'll give should be effective. When we know we are giving these people giving the vaccines to different races and all that, and it's going good, perfect, then we'll move to the phase 3. Here in the phase 3, again we are giving the vaccines to humans, but the large sample size, and the sample size here will be including from 1000 to tens of thousands. But with AstraZeneca it reaches up to 60,000, which is quite a lot, and it's hard to see 60,000 people giving vaccines to them. But with the other Moderna and others, we went with maximum 10,000 with this phase. And again, there is a point about matched demographics that I just explained, so I guess I don't need to explain one more time. Or do I? Do I?
No.
Oh, thank you. So then again, we are on the last phase. We are looking for we are monitoring the symptoms. How we are monitoring symptoms? After this phase, we are just this phase, and then we are asking the people to go for the PCR test who are vaccinated, and if we get positive result or if we get negative result, we have to see accordingly. If we get negative result and see it's effective, then that's the point. After at the end of this stages, we get to what we say, these vaccines went into the emergency use authorization for FDA approval, and that's how the mechanism of vaccines work, and phases of vaccines work. That's how they are made. So I guess it's clear right now. So we should move to the next topic, right?
Okay.
So mechanisms of different vaccines. Sorry for this, but I made it but I will explain.
Okay.
Vaccines mechanisms. So talking about Moderna and Pfizer BioNTech, what happens is this. First I will talk about the virus. This is the SARS-CoV-2 virus. This one I didn't label, but I am explaining right now. Okay, this is the SARS-CoV-2 virus. Everyone listening, right? This is the SARS-CoV-2 virus, and on its surface we have proteins, and the name of this protein is S protein. And This S protein is something against which we have to make the vaccine. So how will we make the vaccine? What do we do? We'll take this protein, S protein, transcribe that S protein into mRNA, and that mRNA we will incorporate into the lipid nanoparticle. This is something what we have in the injection. So when the person is vaccinated or injected on the arms, what happens is the mRNA goes in and this lipid nanoparticle stays out. It doesn't go inside. Only the mRNA goes in and to any kind of cell. We have so many cells in our body, to any kind of cell inside the cell surface. When it goes, this mRNA goes inside, it does not incorporate with this DNA. It doesn't go inside a nucleus and doesn't incorporate with the DNA. What it does, this mRNA will go to the ribosomes, either which are attached to the endoplasmic reticulum or which are found freely in the cytoplasm. This mRNA will go to the ribosomes. This is large subunit and small subunit. It will go, and the process over here, the transcription will take place. And when transcription is taking place, it will produce proteins. And these proteins which are produced are something which are against this S proteins. So these proteins will be expressed on these complexes, MHC2 complex and MHC1 complex. When it is expressed on these complexes, what happens? There is T helper cells and there is also cytotoxic T cells. So first I will explain about T helper cells. This is all histology. I know this might be boring for you guys, some of you guys, but it's interesting, trust me. So T helper cells, this T helper cells has a TCR receptor. This is a TCR receptor. This T helper cells has a CD4 protein. This CD4 protein, when it interacts with the MHC2 complex, it produces the cytokines. These all are cytokines. What kind of cytokines? Interleukins 2, interleukins 4 and interleukins 5. What does these cytokines do? These cytokines will proliferate the beta cells, and when it proliferates the beta cells, what it wants the beta cells to differentiate to. So when it proliferates and differentiates, it differentiates to plasma cell, and plasma cells produce antibodies. These are antibodies, and these antibodies are something which are against this S protein. When these antibodies gets attached to these S protein, it either neutralizes the virus or it destructs it. That means if you are having this vaccine and you get the infection with this SARS-CoV-2 either your immune body, which has these antibodies, will destruct the cell or neutralize it. So there is one more thing. Cytotoxic T cells. This is cytotoxic T cells. These cytotoxic T cells, which also has a TCR receptor, but these cytotoxic T cells have a CD8 protein instead of CD4. CD4, like we have it on T helper cells. Cytotoxic T cells has CD8 protein. This CD8 protein, when it interacts with MHC1 complex, this leads to the destructive molecules, which damages the host cell, or damages the host cell when it is infected with the infection with the SARS-CoV-2 virus. And also it also leads to the production of cytokines, and cytokines, as I said before, it will amplify the process of the beta cells, again differentiate plasma cells, all process will go on. But there is one more point that I'm gonna say. These T helper cells not only make the cytokines, but these T helper cells also proliferate the these cytokines don't only proliferate the beta cells, but they also proliferate the T helper cells to make more memory cells, so that it stays there in the body for long, and whenever the infection SARS-CoV-2 virus come inside, it will just grab and destroy it. Okay, move on. So everything that I explained there in the diagram is all this about. So I don't think so I have to read this. There's no need, right? So this is everything that I just explained there. So there's a diagram about AstraZeneca. So there I talk. Sorry, the name for the technique that I mentioned there, that I talked about in the BioNTech and Moderna, was the mRNA technique. But here it's not mRNA technique, it's a different thing. AstraZeneca, there's a difference between their mechanism. So the technique over here is, like, they didn't mention any name, but I will explain it. Here we have a chimpanzee adenovirus, and inside the chimpanzee adenovirus we have a DNA. There we were having mRNA, not DNA. So we have a chimpanzee adenovirus, which is a DNA. How did we got the DNA? Again, we were having the virus, SARS-CoV-2 virus, and on its surface we were having S peptide. We transcript the S peptide to mRNA, then reverse transcriptase the mRNA to DNA, and that DNA is incorporated inside the chimpanzee. When the person gets the AstraZeneca injection, this chimpanzee will be left like outside, DNA will move inside here in the cytoplasm of a cell, then it will go into the nucleus. Remember, in the mRNA technique, that mRNA doesn't go into the nucleus, but here it is going. So DNA is going into the nucleus, but there is no way this DNA will be incorporating or interfering with the other DNA. It won't. What will it do? The DNA that will go inside will use the enzymes of the transcription, produce mRNA. This process, transcription. That mRNA will come into a cytoplasm, and all this process will begin. They will, under the ribosomes, they will make proteins. Proteins will be expressed on MSC2, MSC1 complex. Then this is T helper cells, cytotoxic T cells. These, and that's all. So don't need to explain, right? Thank you. So this is everything, and when it makes this makes the, what do we say? These are cytokines which are made in response to these complexes. Cytokines proliferate the beta cells and differentiate into plasma cells, and plasma cells make antibodies, and all the way antibodies are against this S peptide, and which either neutralize this virus or either destruct it as a whole. That's all, yeah. And this is once again cytotoxic T cells, which make, like, what we say, destructive molecules to destruct it, or either make the, what we say, cytokines to amplify the process that I just explained. This is all that I just explained. Okay, thank you. So now there's one thing more left. How do these vaccines go by getting efficacy results? Now we'll see Moderna, AstraZeneca, and the Pfizer, like what temperature do they need, what method, like everything. Thank you. So again, I apologize. So first I'll begin with the Moderna. So for Moderna we need 2 dosage for everyone. For every vaccine we need 2 dosage. First dosage we need at day 0. The second at day 28. So 14 days after the day 28, we are looking that person for the symptoms. If we are asking if he shows any symptoms, mild, moderate, or severe. If he doesn't, there is no need for PCR. If he shows, we need to go and ask that guy or girl to go for the PCR test. Then there is method. So this is something, the data I collected, like that was like, what we say, at that time there were, with Moderna there were like 30,000 samples. With Pfizer, like they were just the limited amount of samples that were like taken. So with Moderna, they saw that there were 30,000 samples. These 30,000 people, these 30,000 people were divided into 2 groups: placebo group and vaccine group. So placebo group is something, you can say, the control group, who doesn't get the vaccine. They just get the saline, what do we say, a mixture of salt, something like that. They don't get actually the vaccine. Then there is a vaccine group who actually gets the vaccine. So from this data we go to find that from these 30,000 people, the placebo group who were the control group, 185 people got positive for the corona, and out of 185 there were 30 severe cases for this disease. And when we look into the vaccine group, the people who got vaccinated, actually there were 11 people who got PCR positive, but out of those 11 there were 0 severe cases. So now taking from this data, we will conclude the efficacy, the results against disease and the severe diseases. I mean, result against the disease infection and the result against the efficacy against the severe symptoms. So against disease, we are seeing that there were 185 people in total, like you can say, who got positive result, who didn't got vaccinated, and there were only 11 on the other side. So what we did to make sure how this Moderna vaccine is effective, we will subtract the 185 from 11, 170. So once there were 174 people who got saved because of this vaccine, and in total 185, and if we multiply by 100, this 94.5%. That means this Moderna is approximately 95% effective against diseases, but it is 100% effective against the severe disease, because there were 0 cases of these severe symptoms, like severe cases. Okay, so Moderna is 100% effective. And the storage temperature that Moderna needs is -20 degrees. That's a lot. Like, you need a good refrigerator, and also transportation for such vaccines is difficult, because when you have to transport it to other countries, and you have to make sure that this vaccine is like in that temperature, otherwise it won't be effective, because it needs that temperature. So to maintain that temperature, the cost price will be more and more, because we need good refrigerators for this to make sure that these vaccines are viable at this temperature. And results also shows that the number of vaccines by the end of 2020 were like 20 million vaccines, like sample size, and by the end of 2021 it is estimated that Moderna samples will be in like 1 billion. And same here, I'm so tired explaining. Same here, in the Pfizer there is one difference. We give first dose on day 0 and the second dose in day 21, and after 7 days, not after 14 days, after 7 days of the second dose, we look for symptoms. If person is showing severe or mild symptoms, we ask that guy or girl to go and have a PCR test. Then methods, there were 43,000 people. Again, people were divided into placebo group and vaccine group. Then placebo group, out of those placebo group, there were 162 people who got positive for the corona positive, and for vaccine group there were 8 people who got positive. When I say vaccine group, that means these people were the one who were vaccinated but still got the positive for the PCR, right? And for the placebo group, which were 162 people, 9 of 162 got severe cases, and one of the severe cases were found from the vaccine group. Then from efficacy, results showed that from here that there were 95. This vaccine, Pfizer's vaccine, is 95% effective against the diseases, but it is 87% or 88% effective against severe diseases. On the other hand, if you compare this data with the Moderna, you see Moderna is showing 100% effectiveness against severe diseases, but here we have 88% against severe diseases. So if we just see, we can say, although these Moderna and Pfizer are similar, but this Moderna is quite effective compared to Pfizer. And the storage temperature here we need is, oh damn Lord, -70. Like, it needs more good refrigerators. And Vaccines by the end of 2020 were 50 million for this Pfizer, and by the end of 2021 it is estimated to have 1.3 billion samples of this vaccine. So AstraZeneca, oh my god. Okay, AstraZeneca, the first dose we will give at 0 day and the second dose at day 28. Then after 14 days, here we won't look for the symptoms. What we'll do, we'll go for the PCR test directly. And by this we mean, like, we can also say that people who might be asymptomatic, might showing no symptoms at all, but might have the PCR positive, might be spreading the disease to other people. So here with AstraZeneca, we don't look for symptoms. Even the person is showing no symptom, but still we ask that person to go for the PCR test. Then they were with this AstraZeneca, this vaccine was like given in Brazil and UK, and the result was quite different in two countries. With Brazil, like, there were total 9,000 people, and again they were divided into placebo group and the vaccine group. But here in the placebo group, there is one difference compared to the others. What is the difference? Here we are giving the placebo group the I don't remember the word, meningo, which has the similar composition like the vaccine, but it's not actually the vaccine. And the vaccine group is getting the vaccine. So here on the first day we give full dose to the people with placebo, and the full dose at day 28. In UK, what we did, we gave only half dose on day 0 and full dose at day 28, and this showed the result. That time when we give half dose, even the half dose on the day 0, and here we give one dose, full dose, but even then in UK it showed 90% efficacy results against this disease. I mean, AstraZeneca was 90% effective, and here even it got one full dose in day 0 and one full dose in day 28. It was having just 62% efficacy. So if we just combine the result, we'll say that this AstraZeneca is 70% effective. It is less effective than these two, and if we compare all three, I'll say Moderna is more effective against the diseases. So temperature here in AstraZeneca is quite normal. You can even put in the normal refrigerator, so you don't require a lot of cost for this. So manufacturing cost for this is not expensive. It requires minus 7.8 degrees. I just forgot to mention degree. So it's degree. So number of vaccines by the end of 2021 will be estimated, they're estimating 3 billion. But if this vaccine will be effective, they might plan to go with making 4.5 billion samples of this vaccine. Oh, thank God. And this is something again that I just explained. There's a brief description. There's nothing to explain again about. Okay, so can you move again to the next slide? So here's I guess the last slide. Yeah. So we saw that we can see that from when we give one dose of Moderna, it is 88.9%, almost 89% effective against this disease. And on the other hand, Pfizer is just 77.6% effective. And after 2 doses, the end result, this Moderna is 96.3% effective against this SARS-CoV-2 and Pfizer is 88%. So we conclude from this thing that Moderna is more effective, and the temperature is more devastating over here. It requires minus 70 degrees, whereas it requires minus 20. So I guess this Moderna is more feasible for the vaccines. And that was all. I hope you guys enjoyed my presentation. Yeah, I know it was kind of boring because it was including histology too. And yeah, that was my first ever presentation. I hope I did well. Thank you. Thank you so much.